Thank you for joining me to discuss the ins and outs of each of the science and engineering practices. My name is Eddie Walsh, and I want to start us off by having us consider a phenomenon you could explore if you were discussing an ecological phenomenon happening here in Idaho with your students.
We're here today at the West Hatter Creek unit of the experimental forest. Today we're implementing treatments for a long-term forest research project to evaluate the effects of woody biomass utilization on long-term forest productivity.
This study that we're involved with looks at the difference between removing biomass and retaining biomass.
And one of the things we're doing is we're setting up some long-term research infrastructure for the University of Idaho at the University of Idaho Experimental Forest. It's just outside of Moscow. It's a great research environment, trying to maximize the value of these forests over time for both industrial landholders and private small landholders in the area.
What we're trying to do is to understand the impacts of a bioenergy production system and also try and work that into a program that involves effective and proper management of the forest, where we can thin the forest and see if there are impacts of removing the material and if there are ways to mitigate that removal by amendments.
Having this study set up here, it sets up a great long-term opportunity for us to keep coming back to these sites and studying how the dynamics of the forest change over time.
It's a great example of forest utilization research that has direct management implications for the state of Idaho and throughout the Pacific Northwest. At the same time, we are evaluating some new operational methods for utilizing slash in stand thinning operations. This system uses a gas-powered capstan winch at one end and a block or pulley at the other end to continuously move biomass through a stand at a rate of about 1 foot per second. So it's very slow, but it's continuously moving slash. The great advantage of this system is that it functions like a conveyor. We're able to move 1.5 to 2 tons per hour of material, over 20,000 pounds a day. The production rate is not affected by how far we're moving biomass. So whether it's 100 feet, 300 feet, or 1,500 feet, our production rate stays the same.
If we can develop these treatments and make them economical, it gives forest landowners and land managers another tool in their toolbox when they're managing Idaho forests.
A quick and easy way to get students thinking about what they just saw would be to have them document what they notice and what they wonder about the video they just watched. After some quiet time to work independently, students can share out their notices and wonders in their pairings or groups before collaborating and selecting their top notices and wonders. As we lean into the science and engineering practice of developing and using models, this would be a good opportunity to ask students to consider what they noticed and wondered about the phenomenon that might inform how operations of the University of Idaho Experimental Forest serves as a scientific model. If a student or group of students already began examining or questioning the modeled elements of the experimental forest, be sure you use that student-generated observation to lead into this next part. After having students consider the forest generally, you can then have students reflect and consider what they notice and wonder about the video they just watched, paying special attention to the inputs and outputs modeled in the experimental forest. In the traditional science classroom, students are generally left to observe models in a variety of forms without considering how those models were created or what use the model serves in conceptualizing the many elements included in a scientific phenomenon. Because of this, students can develop misconceptions surrounding phenomena that guide them away from sound scientific understandings. Only with frequent utilization of scientific models can students become more familiar with the strategies used by scientists to model the phenomena that surround us as they extract disciplinary core ideas from their science investigations. I want to go ahead and fully introduce myself. My name is Eddie Walsh, and I am the Region 6 Instructional Science Coach working with the Idaho Department of Education. I'm based out of Idaho Falls, but myself and the other Idaho science coaches are happy to meet you wherever you are in your science education journey. Our sole focus is to help teachers plan, teach, and assess around the Idaho Content Standards for Science. I wanted to take this opportunity to focus on how we can approach the science and engineering practice of developing and using models. If you have further questions about how the Idaho Science Coaches can help you with your teaching goals, feel free to reach out to me at my email or visit our Idaho Science Coach website via the QR code or Idaho Department of Education website. When the National Academies of Science, Engineering, and Medicine developed the 3 dimensions of the framework for K-12 science education in 2011, the science and engineering practices were recognized as perhaps the largest shift educators would need to address to engage students in the immersive experience that is science. Developing and using models to explain phenomena requires students to apply the cross-cutting concepts like patterns, structure and function, and system models while they consider all parts of a phenomenon to further their scientific explanations. The models students use in their science education should illustrate the reflexivity and creativity science researchers adopt as they form scientific explanations. Models can take a variety of forms, satisfying the needs of scientists and engineers in order to test scientific ideas. I would make it my recommendation right now. If you want to get your students to develop and use models independently, do it as often as you can. While students may initially find this modeling to be messy and time-consuming, with practice and frequency, students will be able to make sense of any model presented to them. Frequency and variety in modeling will prepare students for the range of models implemented by scientists to make sense of phenomena. The models scientists develop in the past can help students understand how models have changed as innovations in technology have been adopted and produced new, more correct scientific theories. For example, Rosalind Franklin's use of X-ray technology in her genetic research allowed her to see the structure of DNA. The structure of DNA was not substantiated until she captured images of DNA, which led to the double helix structure that underlies all genetic modeling today. Leonardo da Vinci's famous sketches are excellent examples of how scientists and engineers use drawings to model their theories in untested designs. While not all of da Vinci's models have proven viable, his designs still inspire people beyond his passing over 500 years ago. Sam Traiman's work to consolidate the expansive research in particle physics attempted to explain past and future discoveries in the discipline of theoretical physics. Physicists are still developing theories surrounding the micro and macro structures and origins of the universe, and Traiman's work, along with other physicists, is understood as a fundamental step in modeling all aspects of the physical qualities of the universe. Integrating the science and engineering practice of developing and using models needs to look differently at each step in the K-12 student experience. We as teachers and administrators recognize when one grade band or another doesn't provide students opportunities to advance in their modeling skills, we limit student potential throughout their entire learning progression. If students are not provided variety, frequency, and scaffolding in their learning about scientific modeling, a student who is asked to engage in the messy process of theorizing a model will not know where or how to begin modeling a phenomenon. The K-12 Skills Progression document on the Idaho Department of Education website breaks down the experiences students should be able to navigate to stay on track with peers locally and nationally. This document provides teachers with starting points for imagining a range of student experiences that allow students to build competency in the range of skills associated with developing and using models. When laid out in this way, we can provide clearer feedback to students and scaffold more for students who find modeling to be difficult, or challenge students who have shown early mastery in the science and engineering practice. It becomes important to remember students often do not master a standard in a single instance, so planning several opportunities for students to flex all of their modeling skills within a grade band is critical for all students to stay on track in their science progression. If you are looking for scientists exploring modeling here in Idaho, you may consider walking students through the work of Dr. Karen Humes at the University of Idaho. Dr. Humes considers many variables surrounding earth science in Idaho and models many qualities of the soil, water, and biological processes throughout the state. For example, Dr. Humes has found strategies for integrating new runoff water data points to forecast more regular and accurate runoff outputs through the snowmelt runoff model. This model can help water users in the state moderate their water use to store and conserve water as it comes available through runoff. If you are looking for strategies to bring modeling to the forefront of your teaching, I have a few resources you may consider if you feel this will be a rough start. Modeling does not have to be complex. In fact, drawings on sticky notes or whiteboards are a tried and true method for getting students started in the modeling process. For teachers looking to integrate technology in their modeling, 3D modeling platforms like SketchUp and Tinkercad are simple web-based modeling programs that students can quickly pick up to create digital and physical mock-ups of student-developed models. Getting students to think creatively about materials is a big part of tinkering. Through tinkering, students can think about the materials they use in abstract ways that test and prove validity of their models without the expense of specialized technology or materials. Games like Legends of Learning and Minecraft are popular among students and provide students a free-form sandbox to show their ideas in a form that will satisfy their interest in the social form of video games. PhET simulations provide structure and data surrounding models that students can use to inform their scientific understandings, while also giving students the opportunity to try out digital methods for analyzing phenomena. If making time for science and engineering practices seems difficult, consider going deeper into units centered around modeling and pulling back on content-heavy instructional days with lectures and worksheets. Thank you for your time as we've covered how modeling can help students access authentic science learning opportunities. Hopefully the understandings and strategies outlined in this video make it less stressful to bring instruction around developing and using models to your students. Please do not hesitate to reach out to me or anyone on the Idaho Science Coach team to clarify anything about the standards.